Nitrogen, along with carbon, hydrogen, and oxygen, is one of the building blocks for all life on Earth. Used by plants, animals, and humans alike, life as we know it depends on nitrogen, but not too much. Since the invention of agriculture and our search for ever more productive fertilizers, to the burning of fossil fuels for our humanity's energy needs, nitrogen has never been so important to our success and our survival. Nitrogen accounts for 78% of the atmosphere, and is mostly useless, at least until 1913, when we discovered a way to turn atmospheric nitrogen into ammonia, which in turn improved our soil, which gave us more food, which many thought was quite a good idea. Coupled with the release of nitrous oxide from the burning of fossil fuels, and almost overnight, nitrogen had found a way to become important. So much for being inert. It has been a problem as more and more atmospheric nitrogen becomes reactive nitrogen, upsetting the natural balance of our atmosphere, hydrosphere, pedosphere, and biosphere. Red tides, pollution of our groundwater, and the erosion of our atmosphere is a short list of the consequences of our actions. But there is hope, through change in our actions and attitudes, our technology, and the world around us. One possibility is to think about what we can change instead of focusing on what we can't. As our population grows, and hopefully our affluence, we must look at our technology to reduce our impact. Using our brains and technology, we can have economic growth and a reduced environmental impact. This is the essence of decoupling. In the case of nitrification due to nitrogen-rich soils, nitrification inhibitors can be used to prevent denitrifying microorganisms' exposure to nitrate. By reducing the exposure of the microorganisms using compounds such as itridazole and nitropyrin, the absorption of nitrates into soil can be significantly reduced. This means we can still meet our food demands for the population, keep farmers earning from good crop yields, and significantly decrease our environmental impact. This is one of many potential solutions where economic growth can continue. Furthermore, this can be implemented at a local level, provide significant improvement in local areas, particularly high nitrification risk areas such as wetlands, rivers, and lakes, to prevent eutrophication. We also need to ask ourselves another question with our soil enrichment, not necessarily what we're using, but how. How do we implement these potentially harmful soils, which also provide so much benefit? Nitrogen-enriched soils should be thought of like ice cream, not too much, and only on special occasions. We tend to overuse things that we think are good. In the case of nitrogen-enriched fertilizers, this is certainly the case. In America, farmers are dumping over 80 million tons of nitrogen-enriched fertilizers on their crops. Only 17 million tons of that make it into the food. That's fewer than 22% efficient. That's worse than your car. This is a global issue, causing dead zones throughout the seas, but change can begin locally. By educating farmers and improving the implementations of these soils, we can stop literally killing the oceans. It is possible that we could have a factor 5 energy reduction just through educating farmers here in Australia and abroad. Speaking of education, we can educate ourselves. We can learn from the world around us and take inspiration from nature to solve the environmental problems we create. Nature has an inbuilt survival feature, evolution, the adaptation of desirable traits in organisms, which is essentially prototyping on a scale we cannot currently implement. We can look to the microorganisms for inspiration for the conversion of ammonia to a less harmful nitrate. Nitrosomonas and Nitrobacter are two organisms that literally solve our problems for us. They feed off the harmful ammonia we introduce to our fertilizer, and in turn produce free soil nitrogen. Many questions still surround the process by which the bacteria do this. However, if better understood, then there is potential for a research and development and improvement of our technology to mimic this process in some way and adapt it to more hostile environments where the bacteria cannot survive. Globally, this could drastically reduce the amount of harmful nitrogen entering our nitrogen cycle. We should realize that N2O emissions is not an isolated problem. It is part of the N cycle, part of a very complex system. When working on parts of a system, we can't make changes on one part without influencing others. So here comes the problem of pollution swapping. That is the effect. To reduce N2O emissions can, probably in most cases, result in other pollution, such as NH3 volatilization and NO3 leaching. So management techniques should be adopted to avoid N pollution swapping. Here's a tool to help us: life cycle assessment. When assessing the environmental impact, LCA is a system approach to consider every process of the agricultural work from cradle to grave, taking multiple environmental emissions and all nutrient leaching into account. We can improve our whole system design with the help of LCA. Therefore, to pursue a minimum negative environmental impact on not only one part of the system, but the whole system. There is hope for solutions to the problems and threats to the nitrogen cycle. The ocean's dead spots can be reduced, and the eutrophication of waterways can be avoided through a number of solutions. By using nitrogen inhibitors, we can restrict the nitrification of soil and its exposure to harmful ammonia. We can restrict the amount we use and change the more is better attitude of farmers. Nature can inspire us to convert the harmful ammonia compound into free, harmless nitrogen. Finally, we can change the whole system to a superior, environmentally friendly operation. If we can think about these solutions, implement them at a local level, and adopt global change, we can begin to fix these problems before they render our waterways into one big dead zone.